All right. So again, like I said, what we're going to be doing today is a follow-up from what we did on Wednesday. So you guys did 1.1.1 in your groups. And again, the goal, the whole design goal of that was devising some, not catapult, but general term would be launch device. Your goal is to launch that beanbag only with your given materials as far as possible using what you got and in a certain amount of time. Again, that was the design goal, the overall activity. So you guys should have that. And then what we're going to do today is we're going to take those 10 data points that you guys took for your group, and I'm going to show you guys, you guys have probably heard of box plots, right? Or box and whisker plots. We're going to actually make one of those for your group's given data. I'm going to show you, give you like a crash course on how to make them and what they are, how to use them. You guys are going to make it for your data, and then we're actually going to generate like a standard box plot online for each of your groups, and then put them all in one document. That way you can compare them, and we're going to actually compare all your group's data. All right? So if you want to get your MacBooks out, I'm going to go through it up here. So if you want to follow on here, that's fine. Otherwise, to get to it yourself, which normally you would do, you would get your MacBook out, and again, head to that My Project Lead the Way, log in. It's going to, again, look similar to this. It might not be exactly the same, given that mine's the teacher page. So this will be, again, good practice, how to access whatever activity I'm telling you. It's all going to be housed in this My Project Lead the Way site. And when you get in here, you'll click on Courses. You should have just one. It'll be Engineering. And then you should have just these two. Again, a reminder, this is just a resource page. This is just extra stuff, additional information, more detail, things like that. This, Intro to Engineering Design, this is your class page. That's where all the activities, the challenges, the projects, everything's housed in here. So if you click in here, again, this should look familiar. You'll see this all the time. There's a bunch of introductory material, and then it's categorized by all the 4 units for the course. Again, we're still in Unit 1. This is like the unit start page, and we're in Lesson 1, so the first grouping of kind of activities, challenges, etc. We did 1.1.1. You guys did this on Wednesday. What we're going now to is 1.1.2, which is looking at kind of iteration and evaluating design. Specifically today, we're doing some data analysis with those box and whisker plots. Typically, what you guys would do is, as a group or individually, you would find this on your own. Hey, Drew, are you with us? You would find this on your own, and it's just laid out for you all there. You as a group would be doing this, and you just walk through, and it's got it laid out step by step for resources to look at to set you up, questions to consider, but then also instructions on, okay, what am I actually doing? It's all right here. Right? So what I'm going to do for you guys, this resources is really big. And it's looking at box plots. You're going to make one, but some of you guys might not have seen it before. Some of you guys might not remember it. So they actually have their own resource. Where was it? So if you click this, this launches out to that resources page. Remember there was one that was all resources, one was the actual class. In that class, it links back to the resources to show you this specific one. It's all hyperlinked. And so what I'm going to do here is go through this with you and teach you guys this and make sure you understand this. Because again, a lot of you guys might not know this, might not have had it, but you need to do that today. So that's why I'm taking time to go through this with you guys. How many of you guys have heard of a box and whisker plot? Could you make one right now, by chance? Yeah? No? A lot of you guys, I don't know when they would formally show up in your guys' math classes, or if at all. It's kind of more of a statistic skill. Very simply, it's just a graphical way to show information. So again, instead of having data, a bunch of numbers, you actually plot it on a graph and let visual things tell you information about the data rather than you having to read all the data points and figure out what's going on in your head. Box plots, they use quartiles. Quartiles are a fancy word for quarters. There's 4 quartiles in a box plot. The box plot has 4 quarters to it. Those represent 4 quarters of your data. These are the components. These are the let's see, 5. There's 5 key things that you need to find about your data and calculate in order to make a box plot. There's a min and a max. That's easy. What's the lowest data point you have? What's the highest data point you have? Boom, you have 2 of them done. Does anybody know what the median is or how you would find it? Adrian? Yes. Exactly. This is a bit tricky because a lot of students say, oh, it's the average of the data. No, that's the mean. Mean and median both describe approximately the middle of your data, but mean is the average of the whole data set. Median is literally the middle data point. If I have 5 data points, the median is literally the data point that falls in the middle. So it'd be your 3rd data point. That's a good question. How many data points did you guys have to collect from Wednesday? 10, right? Say that again? Yeah, how do you do that? Because you don't have a middle data point. You have 5 and 5. Well, there's no middle data point. So how do you get that imaginary middle number? Exactly. So if you draw your data and lie it out and cut it down the middle, there's no middle data point. Well, I need the middle data point. I need the median. So what you do, Nolan's exactly right, you have to take the average of the 2 middle data points. That gives you that imaginary middle data point. And now you have your median. So you guys will all have to do this because you have 10 data points. When you have an even number of data points, you don't have a middle data point. So you have to find the average to get that. Q1 and Q3 are probably the ones you're least familiar with. When you look at the graph, these are data points. These are one of your numbers. But Q1, this is the middle of the bottom half of your data. So if you find your median, you have half your data on one side, half on the other. If you look at one half and do that same process, I need to find the middle data point, but only for the bottom half. That's Q1. Again, all these are data points. You just pick them from your list. This one, you're going to have to calculate, but they're all data points. Q3, it's the exact opposite. Now you look at the other half, the upper half of your data points. pick the middle of that grouping, that's Q3. Does that make sense? That's quartile 1 and quartile 3. That's all it means. The middle of the upper half of your data, the middle of the lower half of your data. If that's true, what does this box represent? What do I know about what this box represents if I know what Q1 and Q3 are, like what they're defined as? A more structured question to ask is, how much of my data is represented in this box? Half. If this is half, and I took the midpoint of that, well, that's 1/4 and 1/4. This is half my data, and I split it in half, so now I've got quarters. There's my 4/4 of my data. What this tells me is I can just look at this box and see where the middle 50% of my data falls right away. All I do is look at where the edges of my box are, and I know right away where the middle 50% of my data points fall. I also know my min and my max. I know how far apart they range. Is it ranging from 2 inches of launch to 70 inches of launch? Or is it from 20 inches to 25 inches? The benefit is when you look at this box plot, I can get that right away. If I just had a list of numbers, I would have to find, okay, where's the smallest number? Okay, where's the biggest number? Okay, I got those two. Well, what's the middle value? That'd take a lot of time to figure out. So doing it up front and putting it in a box plot is the reason that this is beneficial. Because then someone can look at your data and easily understand what's going on. Antonio, can I have you pay attention, please? Thank you. Another fancy term, has anybody heard interquartile range? No? It's a very math statistic term. All this means is what's the difference between Q1 and Q3? This range from 5 to 10, from whatever to whatever, the difference is the range. Right? If it's from 5 to 10, the range is 5. There's 5 units from end to end. So the middle 50% of my data is different by 5 units. That's all that interquartile range is. This has a little note. You can put the mean in here, the actual average of your whole data, and you can put it as like a little X sometimes. Some people put an additional line and label it mean to show what's the overall average of my data on this scale. Sometimes your mean and your median will be the same. If you have symmetric data, it'll be the same. But if you have a bunch of little data points and then a huge data point, it throws that off. Your middle data point would probably be one of the small ones, right? But then that huge number that you got, that throws off your whole average. So this is an example where they made this component and the design measurement for this hole, the diameter is 3 millimeters. That's what it's supposed to be. Well, they actually made 10 of them and took actual measurements. You see they're not all 3. There's some variability. So they made a box and whisker plot to represent the consistency of that hole diameter. The first step, again, this is where you guys, this is the procedure for you guys to do this. You need to order your data from smallest to largest. If you write it out in smallest to largest, here's a minimum, here's a maximum. Draw a line, got the median. I know my bottom half, find the middle of that. It goes a lot easier. So you divide it into quarters, cut it in half, cut the bottom half in half, top half and half. You got your 4 quarters. Again, here's your minimum. Here's the middle data point for the bottom half. That's Q1. Your median, it doesn't fall on any number. So like Nolan said, you got to average that and calculate it. Since they're the same, the mean will be the same as the data points. You got Q3. This is the middle of the top half of your data. Then you have your max. You have all the pieces to make your box plot. Then it's just a matter of constructing it. The challenge here, to make a box plot useful, it needs to be drawn to scale. If this is what my box plot looks like, and this is, say, 5, and this is 10, but then over here, this is like, say, 40 to 100, that doesn't make any sense. This is only, 5 to 10. That's 5 units wide. Well, if that's the same size as this, but this was, I don't know what I said, 60 to 100, that's 40 units wide. That doesn't make any sense. And you would have to force yourself to interpret that from the graph. That defeats the whole purpose. If you draw it to scale, this would be really narrow. This would be really large, so you can see most of my data is towards the minimum, and then I have a huge maximum. Same thing when you look at how they're skewed or shifted one side or another. When you draw it to scale, you see that. If all your data, this is a symmetric distribution, you've heard it as like a normal distribution or a bell curve. This is typically what happens in real life. You do statistics and trials, typically it'll fall under a bell curve. It's symmetric. Half your data is on the bottom, the other half is on the top, and they're equal. The number of data points and the values. So everything's symmetric about your box plot. And I can see that visually. This 25% and this 25%, the range is the same, and they're the same size. Over here, I have a ton of little data points, and then a couple big ones. Well, right here, this is 25% of my data in a very small range. That makes sense. I had a lot of data points about this distance. Over here now, this is still 25% of my data, the same number of data points. But they're spread out a lot further. I don't have as many data points in that region, so I spread it out. Again, you can see, in this one you can't even see where the maximum is. Way over here is the maximum, and you can tell that it's very spread out. This is the exact opposite. Most of your data, 50%, is up here. The other 50% is really spread out. Those are things that you can tell by looking at it. Again, the key is you have to draw it to scale. When you guys do this, you just do the best you can, since you don't have graph paper. So you just have to visually look at, okay, my min to Q1, that spreads 10 units. So that's 10. If my box itself is 20 units long, well, that needs to be twice as long as what I just drew. So do the best you can when you're drawing it by hand. This is also some of the power of using box plots or graphical data rather than just a bunch of numbers. You can compare them really easily. And this is what we're going to do. Which of these data sets was the most consistent? Meaning, of all the trials they did, their trials were about the same every time. Trey's saying number 3, right? This one, number 3? He's voting for that one. What else? Other thoughts? Trey, why do you say this one is the most consistent?
Their min and max are closer together. I'm guessing they all have the same amount of trials. So
That's a good point.
and considering it's not as spread out, it's more consistent.
Yeah. I would absolutely agree with that. He had very good reasoning for his answer. He said that the min and max aren't very far apart. 0.15 between the absolute lowest and absolute highest data point. And every other data point fell within that range. That's really, really consistent. Look at this, what's set. 2.7 to 3.2. So that 2 or 3 times more variability or a bigger range. And again, you're right. This doesn't say, but we can assume that all these had like 10 data points. So they all have the same number. But of these 10, they were all over the place. Right? Over here, they're very consistent, very close together. These two are symmetric. About half the data points were above the median and about half below. Here, that's not the case. There's a ton of data points that were, on the low side, below 3. The other half were above 3, but they were spread out a lot. You had a couple extreme, hole sizes that were a lot bigger. If these were 3 different machines, so if I'm engineering this part, remember this guy? If I'm producing that part, and I'm trying to figure out which machine I want to make this part on, these are the 3 different machines. Again, this is what I want. This is what it's designed at. Which machine would I pick, and why? There's a couple different answers to this. Adrian. Okay. So he's saying this is the most consistent. This will give me about the same result every time. There's not a lot of variability. And he's saying, okay, well, the median was at 3.2. I want 3, so something's wrong. And he's saying I would just calibrate that machine or use a smaller bit size, whatever it's doing, to try and bring this whole thing down to be right around 3, so that it's making it according to how it's designed. That's a great answer and then justification for why he said that would be his choice. Would there be any other choices that you would want to pick for this? Could you justify picking any of these other machines for a certain reason? Trey?
I guess you could choose one because if you couldn't calibrate the machine, you wouldn't want to because it's very different.
Good. So in the case that, say, you weren't able to calibrate your machine to change this, you're picking this machine because the median is right at 3. So you have a lot of chance to get right at your design spec. So that again, if you couldn't change it, that would be a great justification of saying we should pick this. We're going to have some variability, but this is closest to our design spec as possible. That's, again, another great reason to pick this. This is a hypothetical situation, so we don't know what's actually going on or why. Could we calibrate this? That'd be the best choice. If we can't, this would be our next best. This would be the worst. The middle, the median, isn't quite at 3, and this has insane variability. Like, it's all over the board. Some of your parts would be too big, some too small, and a huge range. That'd be really bad for production because you might have to throw out half your parts because they're too far off. Another thing you could, in this scenario, you could figure out what are your tolerances. what's acceptable to make this part. If it's acceptable between here and here, 0.1 off, above or below, this is a really good choice. I have almost 75% of my parts are within tolerance. Again, if we couldn't calibrate that, really none of my parts would meet tolerance and be acceptable. I'd have to throw these all out, even though they're consistent. However, if I could recalibrate it, I could get almost all of my parts within what's allowable, so I wouldn't have to throw any away. That's an example of how you can actually use box plots. And engineers literally would do this. They would have to show their boss this and give them their answer. Like, yes, we can recalibrate, we'll bring this down, and we shouldn't have to waste nearly any parts. Your boss, your manager says, thumbs up, put it into production. Like, that's a good design, a good decision. Go for it. Here you could justify the same thing. We're only going to have to throw away 25% of our parts, but I figured out how we can recycle and reuse the throwaway parts. That's what would be, you would have to tell your manager and be a part of your design process in order to justify it and make it happen. Does that make sense? Again, hopefully that gives you an insight on some of the stuff you're doing actually would happen in a business and in an engineering role, and how you would kind of use this and justify it, think about things, and use this to make your decision. This stuff you won't really have to worry about. The upper fence. You guys heard of outliers? There's outliers in your data. Outliers are like just ridiculous extreme data points. Like, they're not even close. They're so far off that they're an outlier, meaning something probably went wrong or something's extremely abnormal. This is an example of, I think it's football player weights. So it looks like defensive linemen. They get all the data and they make a box plot for it. They run their calculations and they find the fence, what's reasonable. There's a data point over here that's outside of that fence. You can calculate that and see this is an outlier. This is way far off. Technically, outliers you remove from the data set. To do that, you can't manipulate your data and pick and choose. You'd have to justify this is statistically an outlier and remove it. But you won't have to do that for this. I'm not going to make it, but I just want you to be aware. There are scenarios where you'll have a data point that you can justify. I'm not going to include this, but here's the reason why. Okay, so 1.1.2, we're not going to do directly according to what it's got written. I'm going to change it. So now what you guys need to do, get in your groups, and you need to get your sheet from Wednesday. It should have your brainstorming, should have your design, your solution, and a sketch, and then your 10 data points. Now what you guys need to do is on that sheet of paper, you can just go on the back, make your box plot, and draw it to scale as best you can on your paper, and make sure you label it. You need to label, this is my minimum, and it's blank inches. All of your units should have been in inches. I had you guys measure in inches. The reason is we're going to compare them later in the class, but they all should be in inches. If you did it in feet, convert back to inches, and make your box plot for your group's data, all right? If you need help, holler at me and I'll come help you out, but take 20 minutes to work through that box plot and get that created for your group's data set. Yeah, Hayden. Is what? Okay. Who's in your group? access computer work, or you'll only need one computer, but at the end of class. So if you can wait, are you able to like just swing by and ask security grab them? Okay, sweet. Okay. You know you can't have tea, right?
It's lemon ice cream.
No, you didn't hear me. You understand like you can't have drinks except water, right?
What is that? It's iced tea, but I was gonna have water. That is the biggest. What? I know that was it.
So again,
It's like a gallon of iced tea.
right? Because I don't know what I'm supposed to do. Because again, that's not school rules.
Some teachers don't care, like last year.
Well,
Most teachers let you drink in class. Like, I brought Monster every day. Like, instead of pouring it out, you can put it in your bag.
Yeah, I was about to say.
Yeah, I think we
There's
need
a way to close that.
But again, like school policy is a water bottle with water only.
Yeah, but there's problems with people.
Get some tape.
Yeah, I was about to say.
I think you need to keep that away as possible. And I'm not gonna send you to the office and have because they're gonna make you dump it out. Because again, that's school policy. Just know in the future, if you bring something in the class to drink, it has to be water. So no monsters, no pop, all right. I'm just, I'm telling you. Oh, you're using it. Wasn't it quad step to start? Let me see if I can. Oh yeah, I can find it. One sec. There. Can you see that?
Oh, I did mine.
Didn't I give it to you on Wednesday?
That's not how you spell my name.
Again, you guys need to remember. You're welcome. Again, if you guys are virtual students and you don't have your username, some of you might not have it set up. Email me as soon as possible. I need to get that to you so that you can get in here and get started as soon as possible. So if I haven't sent you your username, let me know. If not, your password, it's all the same. It's MHS 2020 IED. I can't zoom that in. I know, I'm telling the virtual students, if they don't know their password, it should be, everyone's got the same one. MHS 2020 IED. Again, if you don't have your username for your Project Lead the Way classroom, just like this, email me and let me know as soon as possible. Sorry, you guys. I apologize. They would draw this. Like, you can't tell me that you have to get the support providers. How do you find them? Oh, okay. Again, I want this for both of you guys. Labels and then what we're listening or
Check this.
What's up?
You wanna check this? We couldn't go as far as we wanted. We kind of
Sorry. But it's roughly the scale. Okay, so this would be probably a little small. Right? So this is about 50, but this is actually 40. But this is the rough one. That looks pretty good. As long as you calculated this right. Okay. Okay. Yeah. And as long as all your points are labeled, that's good. Again, just a reminder, on that sheet for your group, I need all of your names on there, and then put what block you're in. So you guys would be White Day, Block 1. Make sure you have all your names and what block you're in. You're going to turn this into me today, FYI. Again, I need all your brainstorming, your design sketch, your 10 trials, and then now this box plot, all in that sheet for your group. Drew.
I seen that earlier. I was like,
This is one of my favorite shirts.
I've never watched it, so I was like, this whole face is so.
Yeah, does anybody watch The Office? What do you mean? Oh.
That's the elf one. That's him as a Sith Lord.
Yeah, this is like his Halloween when he's a Sith Lord.
What is that one?
That one?
Wasn't that when he found the joint in the parking lot?
Yeah, it might be the deputy sheriff when he goes mustache. This is the flasher when Pam draws the sketch. This is they do that rap, the Electric City rap. This is Dwight when I think Jim convinces him that he's in the FBI, but his cover's been blown, so he needs to dye his hair.
Oh, I thought that was Ric Flair. Joker twice.
The Joker, the Halloween, Recyclops. I love that opening.
Stranger.
Yep.
There's the deputy one.
Yeah, that's the deputy. You know this one? That's
when he cuts the face out of the
yeah, the CPR day, and he cuts the face off the CPR doll and wears it, and then Belschnickel.
Yeah.
This one, I can't remember what this is with the mustache. Because this was the deputy sheriff. Now it's going to bother me. Dang it. Yeah, this is like one of my favorite shirts.
I'm wearing
I
a
thought
shirt
the guy
from
with
him.
the blonde hair was Ric Flair.
Hot Shroot? Oh my gosh, that's funny. I've never seen that. That's good. But yeah, anyway, I mentioned that I love The Office, and this is at least some proof that I legitimately do. I own a shirt. I also have Rainn Wilson, the actual actor for Dwight Schrute. He does a lot of like fundraising and philanthropy. He designed a shirt and then sold it to support like women's education in like, poor and impoverished countries, and sold it. And it's Dwight dressed up as a bear holding a beat in, the Battlestar Galactica ship. So the Bears beats Battlestar Galactica. He just made that a picture on one shirt. And so I got one of those a long time ago. But anyway, enough trivia. Drew, I'm sorry. Did you guys need your line swap wrong? take your 10 data, list them like Drew said, smallest to greatest. Okay. So then from here, you can draw a line down the middle. That should mean, well, it's not a data point, so I got to look at average of these. Calculate your median. You look at the bottom half. Your Q1 is the middle of the bottom half, and obviously that's your minimum. You look at the top half of your data. This is the maximum. Q3 is the middle of the top half. Yeah, so you have all your 5 the key points. Now you just draw it roughly to scale the best you can. Okay, so if you guys can get cracking on that, we're gonna, after everyone's got that, we need to move on to an online version. Whoa, whoa. Okay, okay.
Sir, I don't know why you're doing that. That's a bag of chips.
Okay, so again, another thing, if you're on, I need you to let me know, because otherwise I wouldn't implement. But Monday we didn't have a lot. I tried to do accounts for the 3D modeling software. It was a train wreck. Half the kids like it wasn't much to use that. And then we watched like a Tesla. It was from 2012. It ended up being 300. I think you'd like it, but that's all we did for Monday. So that's fine. Your Wednesday, so that's great. Do this. Sorry, I remember you were gone, but I remember. Just want to make sure I'm on the page. Is it an emergency? Alright, what I need you to do, there's a sign out sheet on that card. Just sign out and again, try to be back in. And we'll get going. Trevor, were you guys a group? You guys got your box plot? I think it was done? Cool. Brody, how are you guys doing? Working on it? Need help with it? No bueno? I know it's early, but I'm sorry I'm not more entertaining. Oh, geez. I don't know how to feel about that. In very few circumstances would that be a compliment. Brody, are you just listing them smallest to greatest? Okay, yeah. Once you have that, everything should be easy. Yeah. Mid-max, middle of the bottom half, middle of the top half. Did you guys get yours drawn?
Yes, I know this one.
Does that mean the whole day set?
I just said my mom is.
That's good. Yeah, so I'll try and get you guys going. The next thing I'm going to have you all do is using your means, medians, you want all that. There's an online box plot. So I'm going to have you all make consistent scale box plot. So we're all going to put in one document and compare them. So that'll be the next step. But I'll use this hangout. I'm going to try to get you guys going in a sec. Does anybody else need help with their box plot? Same. Some of you guys might be finishing on your hand-drawn box plot, and that's fine. Try to wrap that up quick. The rest of you guys, I can let you get going on this second part. What I need you to do is go to Google Classroom. You'll only need one in your group. But on Google Classroom, I've got Unit 1, and then this activity, or this material. It's just a shared Google Doc. Actually, let me make sure you guys can all edit that. So again, if you go to Google Classroom and 1.2, all it's got is a shared Google Doc that all of you guys will be able to edit. In there, there's a link to an online box plot generator. What I need you to do is make a box plot through that generator using your statistics. So your min and your max, your Q1, Q3, and your median. What was the largest distance that someone had here? 162? Anybody have more than that? 187? All right, so did I hear 200? 200. All right, you guys, when you get to this online generator, this top is what you fill in. These are all your statistics that you calculated for your data. The title, put your names, that's fine. This, the bottom half, you guys all need to do the same. The reason is they need to be identical so that we can compare them on the same scale. I'm going to set our scale for everyone's. This overall minimum be 0, right? Nobody had negatives, I don't think. 0 to 200 with 25 increments. And then just put inches. It's just the unit. But everyone needs to do this so that we all have the same scale, and it will let us compare each other's graphs. This should be default, 550, 200, just leave that. So put your information in, put this information in, so that everyone's got the same, leave this, and then generate it, and then copy paste. You might have to right-click copy image, and then paste it in the shared Google Doc, so that, and then leave it. However it pastes, just leave it that size, and then we'll be able to compare all of them together. Try reloading. Yeah, I changed the privileges. Like now, there. Right. Yeah. As long as this is your data, that's good. I would right click And then sometimes the copy box doesn't actually do it. What's that? Your group needs. Yeah. Every group's data has to be represented. Just as long as one of you guys gets yours in there. Because then your data compared to yours, and you will kind of see who's got consistent, who's got bias, stuff like that.
We got a 1 inch.
Huh?
We got a 1 inch.
I saw that.
It just went no.
Yeah, you had a huge spread. Yeah. And if this is scale, you have a big skew. A lot of data is here, and then the other half is really spread out. You got yours? Okay, if this is all your correct data points, I would right click and copy that picture. Do copy image. I don't know if that'll work. You can try it. Other classes it wouldn't. You two finger like. Sometimes you do it. And then paste it somewhere in there. Then that's good. Does anybody need help? Guys, can I have you put your phone there, please? Huh? If you right click, copy image, that sometimes works better. If you click the copy button on that site, it doesn't actually do it as well as I thought. On your agenda. It looks right. Oh yeah, your title, put your name. It's not a huge deal, but and then just regenerate it. Once you get your box plot in that doc, then hold off. As soon as everyone gets it, we'll look at them all. Has everybody got their generated box plot in this Google Doc? You guys got yours? Has everybody got theirs in? Drew, did you get your guys put in? Okay, so everyone should be in this doc, right? Again, if you guys are virtual students, you don't have to do this doc thing, but just look at these results and we'll walk through them together. So now the big question is, we all have a box plot that describes your group's data. We've all put them on the exact same scale. What this is going to let us do is easily compare each group's data to each other. So I'm going to just take a quick scroll through and show you guys all the different groups and what their box plots look like. Tyler, can I have you stop editing and just leave your picture in there? I think that's it. 1, 2, 3, 4, 5, 6. We're missing one of them. Somebody needs to put theirs in. So now, Drew? Yeah, if it's on a 0 to 200 scale, but yours only goes, 50, it can't write the text, so that's fine. Again, keep your mask up, please. So again, when we look at this, we can start comparing each group's data to each other. You see, there's a lot of differences in every group's data. Which group technically won this goal? Like this design challenge? What was the goal of this whole design challenge? Yeah, the maximum distance. So which group won or had the best design in this class? I see this guy, right? 187. This was the highest data point. So according to the design challenge, that group had the best design because it best accomplished the design challenge or the goal in the time constraint and using the constraint. So kudos to you guys. Now we can think about, what did we design? Like, in a general sense, what were you guys making? A launch device. That's a super catapult. Not everybody made an actual catapult, but a launch device. We're trying to launch something. The goal was the maximum distance. But is that actually the best design goal or the only criteria we would want in a launch device? No. What would be another criteria? Consistency. That's pretty important. I would want to know if I'm going to use this device about where it's going to go. You know, they had quite a bit of spread from 70 inches to 187. If I'm using theirs, sure, they had the maximum distance, but it also, there's a lot of variability. How about this group? Right here. What can we say about their device? Well, the best in what sense? The best in consistency, you're correct. There's no other group that had, this group's pretty close. About 40. There's only 30. This group is the best in terms of consistency. All 10, you guys all did 10 shots. They all those 10 launches, they happened within 30 inches of each other. This is the most consistent launch device. Okay, now if I think about, if this launch device, this model we made was to be produced as an actual, say we're talking old-time war, we need some sort of catapult or launch device. That's the best weapon we have. And I'm going to war, and I have these different companies. They've given me their data for their launch device, and I'm the Army and I need to pick one. Which one do I pick? I see some people want the most consistent. Hey, who wrote this? It said Kyler.
I'm not even on the document. I know that for a fact. I'm literally in Google Classroom and I didn't write that. But it had your signature. Yeah, I know. That wasn't me. Sure, it was edited as Kyler Mumford. Well, is that your name? Yes, it is, but I didn't write it. Who wrote that on your computer? Nobody wrote it on my computer. What I'm saying is simply I was hovering over an object that was right here. It was this weird symbol right here. And then somebody changed it while I was over it.
I'm gonna look in the history because
You can go ahead
if
and do
this
that,
is gonna
because
be
I
a
didn't do it.
problem for you guys, that we can't act as adults and be mature and do what we're supposed to, we're gonna have issues. I don't want issues, but it's a problem that was written. There's no reason for that to be written. And there's no reason that any of you are not mature enough to know that that wasn't a good decision. Yeah, there's no reason for that, you guys. And now I've had to take class time to address that. And again, there should be no reason that I would need to do that. So back to what I was talking about. If we're actually designing something and we're looking at some catapult or launch device for military, one of the suggestions was to choose the device that's the most consistent. Now, a lot of times this depends on what you want out of the device. What's your actual goal? If your actual goal was, like this challenge, the max distance, well, that's easy. The data tells me this is the best device. The problem is, if you're taking this to military, it could launch half the distance, or sometimes it'll get the full distance. But you won't be able to rely on this device very much. There's a trade-off. You have the max distance, but you have a ton of spread. Drew.
Because let's say you were aiming for a special area, you wouldn't want to, let's say, shoot it and then it not even go anywhere near there and go past it.
Exactly. In this situation, a launch device or a catapult, you're going to be aiming somewhere. If you don't really know where it's going to actually land, you're aiming somewhere and it could be anywhere from here to here. That's not going to be a very useful device to you. Down here, this will be a very, very reliable device. The data points are showing me that there's not a lot of change in every launch. 10 launches, they're all going to be within 30 inches of each other. Now, if this is the actual device, say this is 30 meters. Very consistent. So I'm going to be able to aim and know I'm going to get pretty close to where I'm aiming because it stays in a very predictable range. Now, the trade-off is it doesn't go very far. So, someone might argue, I want this device. It's not as consistent, but it has more range, right? So if you are designing something or using another part to make your design as an engineer, this is kind of that cost-benefit analysis. You're optimizing. I need to consider a lot of different things and say, what's the best combination? The best distance with the best consistency. If I get the best distance, I have no consistency. If I do the best consistency, I don't have a lot of range. There's trade-offs, and you would have to figure out what's the best combination of all these things. Again, the point of using graphs, using statistics and visuals, we all did this. Each group did only one box plot, and now we can compare all of them. So I can look, if I were the one purchasing the device, I would look at all your designs and I would look at your data and I would be able to make my decision like, yep, like this is the one I want because I value consistency. That's what I would pick. If I say, nope, I just want the farthest one, boom, that's the one I'm picking. I'm buying that device. Now, as your manager, that's probably what he would do. They would think of like this is what we value. We need the best. We're going with this. Or like, no, we need a reliable product. I'm going to pick this one. Again, you can determine, this is just your numbers. This is what it is. This is what your device can do. You determine what's important. How do I pick that? How do I balance a couple different things and get the best of all aspects or all criterion? And I pick those. Hopefully you see the benefit not only of just graphical data. I don't have to sort through their data and see like, okay, it can only go this far. There's that data point. What's their average? Oh, I got to calculate that. There's their average. Where does the middle 50% of their data fall? Like, how close is it? If this is all graphical, it's easy. It's much more useful to have this than a list of data points. And a lot of times, you're going to need that to figure out if your design is any good. If you get a bunch of data, you need to figure out if it's good. Well, make this, and it tells you, and you have proof. You have evidence to support that. It also lets you make decisions. A lot of times in engineering, you have to make decisions and optimize your decisions. These are great ways to do it and great ways to compare. Does that make sense? Hopefully that's helpful to see how you can use data to make decisions and find useful information from a bunch of numbers you collected, but also see how when you make designs, you gather data to prove certain skills about it. You can use those to make decisions. Again, we'll get a lot more in depth, especially when you guys have your own projects. You'll have an open-ended goal, a long period of time, and your resources. You might have a couple criteria. So you might do this for different distances and see how close you can get. You can do different criteria and put it all together to make a decision across a bunch of different categories. It also shows why data analysis is useful and how easy it was to compare all your guys' groups from a couple images. Any questions at all about this launch activity, the box plot, the data analysis? Any questions on how to make the box plot? Like, would you guys be able to repeat that for a different data set? No? What's the first step? If I give you a bunch of data to make a box plot, what would I do first?
Divide them up into your quarters.
Yeah, how would I do that?
Get your median.
Yeah, put them in order. If you put them in order, you have your min and max. You cut the data in the middle. One half is your lower half, one half is your upper half. If you look at the lower half, take the middle of that. That's Q1. Look at the upper half, the middle of that's Q3. If you have those 5 data points, the max and min, let me show you one. If I get the min and max, if I get the median, in the middle of the upper half and lower half, I can make my box plot. It's really easy. Hopefully doing this helped you show how to do that process. Any other questions? All right, you guys finished early. What I'll give you guys is basically a study hall. So feel free to work on stuff. If you don't have homework at this time, I'm going to give you guys permission to be on your phones if you want to. It's up to you if you want to use this time to work. You can get on your phones. Yes, what I need from you before you do that, each of your groups needs to turn in your sheet. So it should have, again, all of your names, first and last. Yeah, it'll help me when grading. It needs the block, so white day, block 1. It needs your brainstorming. It needs what solution you chose and a sketch of what you built. It needs all 10 of your data points. And then it needs your box plot, the calculations, and the box plot you drew. And have all those key points labeled. I need to know what was your minimum. I need to know what was your median. Once you have all of that, that's what I need you guys to turn in. 1 for your whole group. And that's what I'm going to grade. And then I'll get those back to you. All right? Got all? Okay. Where do I put it? I'll come around and pick it up.
That was a terrible guess.
Nice today, yes. Oh, okay. Is this your guys'? Is it all done? Yes. One second. Anybody else's? Whose group? Is this your guys'? Is it all done?
I don't know either.
Okay. Yeah, I'll be with you guys and let you do that. Anybody not turn those in? All right.